Ladies and gentlemen, please welcome our next speaker, Anurag Kale, presenting the topic, Building Data Lake Platform Fully Serverless.
I'm going to try to be a little more entertaining than usually what I try to do and try not to bore you to that. All right, quick questions before we start. How many of you have here heard the word data lakes before? Okay. How many of you built data lakes before? Awesome. Have you done this on AWS or something else? Okay. Couple of them. What does serverless mean to you? I mean, that's an open-ended question, so maybe just shout out. What does serverless mean to you? No takers? Exactly. That's a good, let's say, summary of how you should perceive serverless. So this is what we are going to do today. Let's assume that you are a engineer, perhaps a senior engineer or you have been an engineer working at a company and you have been now given a new task at hand, and it's an open-ended question, and you're trying to solve that particular question for the company. So before the ChatGPT world, what you would do, you would go to Google and try to search certain things, right? So you are given a certain problem statement, and you go on Google and you say, try to search data lakes. You will find something like this popping up every here and there. So this is taken from AWS's website. It's a great architecture, but you will see that there is plethora of services that are moved around, and I'm the kind of person who would want to understand the paradigms of data lake before I go on into the details of the services. So I continue my web search, and something like this kind of pops up, where they are talking about various blocks and pieces of, let's say, pieces of systems that are talking about it in the data lakes. You continue searching, and you might stumble upon something like this, which basically is talking about patterns of how data lakes should be done, right? Now, we need to understand that software architecture is very nuanced topic. Everyone, which I mean is me, we are dealing with different constraints. So some things that are important to you might not be important to me. So when you look at an architecture pattern like this that I have shown you on the screen, it is not fine-tuned to your use cases. It's not a solution architecture. Similarly, when you look at reference architecture, it is basically a set of services that have been built together that can give out a generic capability. Both of these pieces are really, again, they are really important for us to understand the services, how these various AWS components work and all of those. But what we really need as an engineer is we need to find a solution to our problem statement, right? So you need to cut the noise out of all of these diagrams that you saw and just pick what is the best for you. Pick what is the best according to your constraints, and that's my intention for today. So I really want to talk about the problem statement and what is it that we did in order to reach to that particular goal. Before we go there, a little bit about who I am. My name is Anurag, and I currently live and work in Gothenburg in Sweden. I work for an electric car company. Unfortunately, I'm not allowed to tell the name, but you'll figure it out later. And I'm also something called as an AWS data hero, which is like Microsoft MVPs and of that kind of sorts. If you're interested to talk about data lakes or data in general on AWS, feel free to connect with me on LinkedIn, and we can take the conversations later. So this is the agenda for today that we are going to try to do. We will talk about the problem statement first. What is the problem area? What are the constraints that I'm dealing with? I will also talk a little bit about the framework that I used in my mind in order to choose or reach to the conclusion that the data lake is the right paradigm for this kind of use case. I'll spend a little bit of a time to walk through the solution that we are using and why we made certain choices during that particular phase. And I will try to, again, I will nothing promise, but I'll try to give certain takeaways or certain things that I learned during the process that might help you in your next journey if you're going to try to build a data lake for yourself or your company or your assignments. All right, let's talk a little bit about the problem that I had at my hand. So I was working at a company where the landscape was very diverse. When I say diverse, so the internal landscape, which is basically what we also call as a trusted space, because I own the entire application, we had a bunch of products that were built in-house, and they were all built using serverless technologies. So all the components, all the APIs, all the orchestration, everything was serverless, and everything was event-driven applications. So event was the first-class citizen that we were using for exchanging information between the systems. But at the same time, we already also had a bunch of commercial off-the-shelf products that you buy off the market. Example SAP, example Workday, example multiple of these automotive manufacturing MES solutions that you just buy off the shelf and you try to make it work. We also had a team, data and analytics, who wanted to collect the data from all of these, let's say, things, and information security, because we were a company that was listed on NASDAQ. So here's what happened. So then what we did is there is also multiple partners that we are working with. So these are manufacturing partners, these are delivery partners, and these are people like Stripe, who are, let's say, processing the payments and stuff. So we had plenty of those partner systems, SaaS, managed platforms, and even factory systems where the cars were being produced. That is something that we didn't control. So naturally, we wanted to get the data which is in untrusted space, and we want to bring it into the trusted space so that we can make use of this data. So like in any startup-ish phase happens, everything went berserk, and people started building integrations towards these external systems, and soon we had a spaghetti mess of integrations. And typically in an enterprise setup, again, I say startup and enterprise, it's a weird setup, but it is a weird setup. So in this setup, wherever there is an integration, they will go and pick up a enterprise service bus of the market and try to build these integrations. Now, it might work okay, but in this kind of setup, I'm now not even representing all of the applications that are involved, and it still looks a mess. And I had 60 different products that were built in-house. We had 10 different COTS product that we were building, and each of these integrations might have had like 5 to 10 pipelines. So you could imagine. So this was like we were going through a nightmare. We lost the raw data every time somebody made an ESP connection to the external world, because they took the data what they wanted, right? So I only wanted 5 attributes out of the external partner, and I'm going to ignore the rest of the 5 or 15, let's say, message components. So we lost the raw data in the process. This was a governance nightmare, of course, because nobody knew what kind of money are we paying for the external systems, because everybody had the freedom to build their own integrations. At the same time, the boundaries of these integrations were unclear. So if, for example, if I take a payment SaaS, so the data about payments is required by the ERP system, it is also required by your order system, it is also required by your, let's say, invoicing system. So all of this built the 3 individual pipelines towards it, and it's basically who is exactly owner of that particular pricing object. We were not able to place that, and this information is critical if you are trying to establish ontologies, if you are trying to establish the in general data landscape in your organization. So it was very problematic, and this kind of created a big process waste in the process in this entire thing. So what we really wanted to do, we wanted to change this. We wanted to take control of these situations, and this is where the problem statement kind of started. So these were some of the desired outcomes from this process, or for this project that we had in mind. We wanted to standardize the data ingestion, because we wanted to have a fixed governance way in order to predict how much cost are we going to pay for the external people in order to get the data in. We wanted to have better governance. Of course, who doesn't want that? We wanted to minimize the process waste so that you don't wait for the vendor to return back to you in 5 days when you're asking them for a new data object. And we wanted to build something which would help multiple personas. These personas being developers, business analysts, data scientists, so that they can utilize this data and not lose the value of this data. But there were certain technical constraints. There were certain budgetary constraints that we had. So due to that, we made 3 critical choices: that we are gonna build this particular platform as a data lake, as a self-service based platform, which basically means minimal involvement from the humans to get the data in or out of this particular platform. That was my first constraint. Second is because it was a very small team, we had to build this frugally. So we wanted to make sure that we don't pay upfront very much. So we wanted to have some sort of a OPEX model over CAPEX model. That's why we chose serverless. And it had to be built as loosely coupled system, because although this seems like a project that came from top down, this was a project that was built bottom up, which basically means engineers saw the problem. Engineers thought, okay, this is a problem and we need to fix it. So I needed to build a system that would evolve over the time. So it has to be loosely coupled in theory. So if I forget about the technical constraints, if I forget about budget limits and anything, right? So if there was a magic wand that I could just push it and build some sort of a solution, what kind of black box solution would we think about, right? So this is what we thought. So we had an external space, internal space. How about we build a centralized data ingestion platform? And this platform, that's the black box that we're talking about. And it needed to have certain attributes for it to work, right? It needed to have integration options that could integrate with these external partners and push support to the maximum possible permutation and combinations, so that the external we can integrate with the external systems. Now, once the integration happens, we needed to store this data so that, again, we didn't want to lose the raw data, right? So we wanted the possibility to store this data somewhere. Once you do the storage, you want to make sure that the governance is intact, and it needed to have a governance pipeline. And we also needed to have distribution options, so that the rest of the systems downstairs, which are in our systems, which require different mechanism themselves, we should be able to provide those options out of this black box. Then basically we went, I was a young architect, I went on, we started to question, how can we build this particular black box? What kind of terminologies can we use? What are the different options? And if you're working in enterprise generally tends to default to a data warehouse. Everybody's like, hey, we need a data warehouse for this. But there are some inherent issues with data warehouse that I'm going to try to address, and why it is not a good solution for this particular problem. So what kind of architecture patterns can we solve this? Again, at the beginning I said I tried to be the first principles guy, and I'm like, okay, before even getting into the details of a data lake, data warehouse, you should really think about this problem from first principles. And I started digging around and ask some questions. How is it that people decide which is the right paradigm, right? So this, when I digged around, this is the summary of what I found. There are essentially two different approaches to get data from value from data. The first approach is a top-down approach. Now, in this top-down approach, you have the data, you have some sort of a theory that I want to get and you have an hypothesis about this, which is basically I want to make, like, let's say an example, if I use data, I will be able to streamline my processes. That's an hypothesis that you make, right? Now, to make that hypothesis, you do some sort of an observation on the data that is available, and then you get a confirmation. That's a top-down approach, right? And this top-down approach, then there is also another approach which is bottom-up, wherein you don't have a theory at this moment, but you know that there is a lot of data available. You know, so you can observe the data. Once you observe, you start to see some patterns inside of this data, right? So once you see the patterns, then you say, okay, now I see something, and there is some kind of hypothesis in this data, and then I'll make a theory out of it, right? So these are two different approaches. The top-down approach is what data warehouses uses, because when you're trying to build a data warehouse, you're in control of the source, you're in control of the target, you know the structure of the data, and now if you think about it, how you build your ETL pipelines, you will see that it's a top-down based approach. At the same time, if you're doing a bottom-up kind of approach, you will see that when you typically implement a data lake, you're implementing a bottom-up kind of approach, where let me take the data as much as possible, and then I'll decide how to do it. So basically, these were the two theories that we had at hand. You use top-down approach when you know the question that you want to ask to your data. You have the data, and you know the questions that you want to ask to the data. Sure, it's a little meta-reflexing right now, but if you think about it, that's how BI systems works. If you do data warehouse, you have to do a lot of upfront work. You have to figure out source schemas, you have to figure target schemas, you have to do data modeling, right? So this approach is what I call as schema on write approach. So before writing the data anywhere, you already need to have the schema. But on bottom-up approach, what you do is you basically don't have a question right now, but you know that you need this data for something later. You will be doing little upfront work, and you will do schema on read. So you'll put the data and put the requirement on the consumption systems to figure out what the schema is. Overall, if you think about my constraints, what kind of things that I was trying to achieve, and what data lakes gives us in this theory, it was natural for us to choose a data lake as the paradigm for of choice to build that black box. Now, being that first principle guy, I'm like, before even I go there, let's try to understand what the hell is data lake. What are the building blocks inside of the data lake? So this is what, in summary, what data lake is essentially about. At the heart of data lake, data lake is a paradigm that was born from cloud. And the heart of the data lake is an object storage. And object storage is basically your S3 or Azure blob storage or whatever equivalent of GCP is. And that is what you use as your place of storing all the data. In data warehouse approach, you use a fine-tuned relational database. Similarly, replace the fine-tuned relational database with an object store, you have a data lake. That's very simplistically. Now, to use this data storage as, object store as data storage, you will start getting data from databases, IoT devices, applications, disk, flat files, whatever you can imagine. So data lakes, actually, because they are just flat files, they support multitudes of ingestion algorithms. So you can do ETL, you can do change data capture, you can do uploading, streaming, yada yada. So it supports multiple paradigms. Works really well for our use case, because the systems that are going to send the data from outside of my control, I don't know what kind of ecosystem they are going to use. So I can, if I use data lake, I'll be able to fine tune it for my use cases. Now, once, let's say, the data streams in and it's in object storage, because it is flat files, if you have millions of files, you will really don't know where your data is, right? So you need better ways of discovering that data. So a data lake at heart should also have something called as a catalog, which basically tells you what kind of data I have. And if there are frequently used access patterns, you should have indexes on top of it so that you can speed them up. Now, from the object storage, to build this catalog and this index, you need some sort of computing, right? So for that compute layer in a cloud ecosystem, you will use function as a service, which is AWS Lambda or equivalent, or SQL as a service, like some services like Athena. That will take the object store, derive the metadata out of it, and build that catalog for you, or keep that indexes fresh, right? Now, so far, I'm able to put the data into the data lake. I'm able to make it useful. Then your rest of the ecosystem can start taking data from it. So you could build reports, you could build dashboards, you can, or maybe another database or another data warehouse can take the data from this ecosystem, and it supports multitude of protocols. You can do batch operations, you can do ETL, you can do SQL as a service, or you can just plain read the files using file operations in any language of your choice. So far, data ingested, data curated, data provided to the rest of the ecosystem effectively. But if I don't manage this, if I don't keep an eye, I don't keep a lid on what's happening inside this ecosystem, I'll have a governance nightmare. So I also need to have what I call as a governance layer in the data lake. On this data lake governance layer, what it will do is it will have identity and access management, so that we can provide users certain limits on what kind of data they can access. I also need to have policies, because without policies, identity and access management doesn't work. And you really want to track the lineage of your data as well, so that you know where the data came in, where it went out, and you can have the entire life cycle of the data mapped. So overall, looking at what I wanted to achieve and how data lakes are working in first principles, this seems to be a great choice. But now this is very generic in nature, right? This is the reference architecture. This is the stuff that I was talking about. So what we are going to do, spend next few minutes, is take this exact building blocks and try to fine tune it for our use case using AWS components. So let's try to implement this using AWS services. So then what we did is we broke down the entire system that we wanted to build into 4 logical blocks. The first block was something called as a landing zone. Again, this is all in my head, right? This is not physical. This is like for us to understand. That's a mental model. So we need to have a landing zone, which basically is a layer of software that allows integrations through external world, which you can fine tune depending on what kind of services your external world provides. Now, once the data lands into your ecosystem, we want to build a storage layer. Once the data is stored, managed, curated, you need to have a distribution layer, which again, this distribution layer needs to be fine tuned for your landscape in your controlled area. And finally, I need to have a control plane. So what we are going to do now is we will go deep into each of these blocks and try to build them together. So this is what we did. So in landing zone, we decided that we will use a streaming service, because the systems that are going to send me the data, they don't put it on a cadence. They send it when it is available. There are so many multiple systems. So a stream seems to be a logical choice where the data can come in and converge. So as soon as the data comes in, I send this data to a stream processor. Again, we'll go into the details. This stream processor makes 2 copies of this data. The first copy goes into a data lake, which is going to be kept for historical purposes. And the second copy is put in a temporary data store, because I immediately want to send this data to an event store. So the people who are event driven get the messages in near real time for their consumption, right? So this was like majority of my components that were built in-house were serverless event-driven applications. So I'm serving the biggest customer for my internal landscape. So they, as soon as the message lands in, puts it on a stream, we make a copy, temporary copy, permanent copy, and the message is received by the serverless or commercial or internal inbuilt event-driven architecture. Now, for some of the when you look at streams are inherently have some limitations on the amount of message that you can send at the same time. So we needed to try to build a system that could also allow for messages that are bigger in size, like 20 MB file, 50 MB file, 100 MB file that still need to be processed. So we had to build something called as a file uploading mechanism that would allow you to put a file. And then we also had this historical data needs that perhaps will be required by some of these applications later. So we were able to build this logical, logical way of building this application. So with the near real-time delivery, I'm able to support all of the applications that are event-driven. With the historical data that is available, you can use Python, and you can use ETL queries that will allow applications that are 20 years older, which cannot do event-driven architectures. They can still bring the data out through API actions or through ETL and get it to the ecosystem. Now let's try to go into the component design of each of these. So for the streaming, we are now diving deep into the AWS ecosystem. For the streaming ecosystem, we essentially had 3 choices to make from AWS that were fully serverless and matched our criteria. They were Kinesis data streams, there were Kinesis Firehose, and there was Kinesis Analytics, which now has been changed to as managed Flink. But out of all of these 3 options, only Kinesis Firehose is fully serverless, which basically means I need not do any configuration, I need not do any provisioning. It will just work out of the box if you are using. So Kinesis Firehose became the first service that we chose because it allowed streaming for the data in. Now this is where we hit our first problem or first challenge. So some of these systems, although they were able to send us messages, they were legacy systems. And for authorization of Kinesis, whenever you use AWS services, you have to use something called as a simple token service, STS, or AWS users. So the legacy systems could not use STS because STS is like a dynamic token vending system. So what we had to do is we had to figure out a way to work around this issue. So what we did is we just put a small API gateway facade in front of it and used AWS users from IAM. And IAM users can have long running tokens. So it gives you an equivalent of username and password that can then with your policy you can keep it alive for 1 month, 6 months, 1 year, or never. It's not ideal, but if you have legacy systems in your ecosystem or in your vendor ecosystem, you have to have it. So this is how we designed the first component of the landing zone. Now, if you look at Kinesis Firehose, the Kinesis Firehose also has a little bit of a limitation that it can only process a message that is only 256 KB in size. So if you have a message that is more than 250 KB in size, and if you look at text which is greater than 256 KB, it's huge data, it cannot process that particular data because the rest of the ecosystem in AWS, like SQS, EventBridge, or all other API integration services, their limit is 256 KBs. So we needed to find a way in which if the partner systems are sending us data which is bigger than 256 KB, we need to figure out a way on how to make that possible. So to do that, we built this, oh, sorry. Yes, here we are. So we had to build a file upload mechanism. Now to build this file upload mechanism, what we did is we brought together a bunch of services that worked in a flow. So we had an API gateway where the external partner would tell in the first thing that I am this service and I am intending to upload some data that is bigger than 256 KB on your system. So we take that service and we record that in a Dynamo database, which basically says, okay, this guy or this system at this time is trying to upload. And we capture some metadata from them, which is basically who you are and what kind of data are you serving. At the same time, we trigger a Lambda function that goes into S3 and returns back with a S3 signed URL. Now, if you are not aware, in S3 there is something called as a signed URL, which basically creates a link to the folder inside of S3, which is valid for a certain amount of time. Imagine of this like a Google Drive link that you share to your friend so that you can upload a file on that particular link. So something similar but programmatically created. So then at the step 5, we sent back this S3 URL to the caller or the client, and they took this particular S3 URL with the tokens and service and authentication and all we gave, and sent that message directly to S3. So you can upload through a signed URL, you can upload the message directly to S3. Once the message lands in the S3 folder, you can use AWS's S3's native functionality of event notification, and it sends a notification saying that a new file is available at this particular link in S3. But if I only give that notification, my downstream applications will not know which kind of file it is or who is sending this file. So in this process, what we did, in the previous step, in this DynamoDB, we did capture some of the metadata that we had. So we took the event notification that S3 created, we took the message, the metadata that DynamoDB had, and created a notification, custom notification that we could send downstream. So this was my component design of the landing zone, right? Now, once the landing zone was complete, we needed to build the processing and storage zone. So for stream processing, when I do stream processing, I use Lambda. Lambda triggered this message. Lambda made a copy of this message in a DynamoDB, which served as a temporary storage with a time to live for only 2 days. And we also made a copy in an S3 bucket, which was the data lake. Now, if you remember from the previous setup, when the file upload functionality completed, S3 had the file, we got this message, and we triggered another Lambda, which put the message on event bus, basically saying a new file from this particular system is available for your consumption. And essentially then you can also use ETL, you can put an ETL on top of the S3 bucket for your bulk data needs. Now looking at the distribution mechanism, so for event distribution, we use something called as EventBridge, because in EventBridge, what you can do is you can configure rules that are dynamic in nature, which basically can look at the contents of the message and say if the message meets certain criteria, it needs to be forwarded to this particular endpoint. You can configure that. So we use that. And for ETL kind of use cases, we use something called as AWS Glue, which is managed Spark runtime. Now coming to the control plane. So in order to make sure that the data is readable and we have a catalog, we use a service called as AWS Glue Crawler. The crawler basically goes into your S3 bucket and looks at all of the files and derives the metadata out of it. Basically, name of your columns, what kind of data type do you have. It crawls it and creates a schema for you. Once the schema is available, that schema is put into a Glue data catalog, and this Glue data catalog is used internally by Athena that allows you to do SQL queries in place in S3 on your data. So with this, we were able to enable in-place querying for the analysts. And for managing role-based access controls, we use something called as AWS Lake Formation that allows you to register this S3 bucket as a lake, and you can do role-based access control by using IAM, which is built into Lake Formation. And then for some API-oriented designs, we used a simple API setup that allowed us to do that. Now this is where we hit the final challenge that we had, which was that if you are taking the data from Kinesis streams through and Lambda, putting directly into S3, S3 creates a combination of files which is broken down by year, month, date, and hour. So if you collect the data from various systems in a single place, Glue Crawler gets confused because it gets message formats that are different for different systems. So what we needed to do is we needed to figure out a way in which we can dynamically break down the message into the specific subfolders inside of S3 so that it is collected together for us. If we do this, so an example, all the messages from Stripe should go into S3/Stripe so that the message will remain mostly consistent. Again, it's okay to have 1 or 2 columns that are missing, but it remains mostly consistent. If you have another endpoint which is coming from, let's say, another payment provider, you will have S3/ that payment provider's name, and the messages will be collected inside of that. But for this to happen, we needed to put the enforcement on the source systems to provide us data in certain format. So for that, what we did is we created this metadata data kind of format. So whenever you send an event to us or a message to us, you append this metadata tag to any data that you're kind of sending. Now using this data, then we use this source and resource targets to create subfolders inside of S3. So all of the messages that are coming from one particular source are collected together in a single subfolder inside of S3, and then Glue crawls it over and treats it as a separate data source. So this was the outcome of all our exercise. This is how it looks together in the entire process. So sure, this is how it looks today, but it's not the end. I said that I wanted to make this as a self-service platform. I want to ensure that there is minimal human involvement when you want to use this particular service. Some of this stuff we have already did, but I just want to let you know. So what we wanted to do is we wanted to automate onboarding for the new producers. So what we did is we worked with our ServiceNow team for the legacy systems. They can make a ServiceNow ticket, which is auto-approved. As soon as it is auto-approved, it goes through an it goes through an AWS account, creates an IAM user for them, and returns the credentials of that IAM users. For systems that can do STS, we created a common GitHub repository, and they can make a pull request. The moment they make a pull request on certain criteria, they will get back a STS role, and that they can assume and build it. We also wanted to onboard the consumer systems, so we created an API action that was a facade on top of event bridge rules. So basically, you could send us rules that we would register in back of us. We've also want to add a service called as Glue Data Quality, which basically lets you define quality checks on the data that is coming from the source. So you can put something like, if the data is coming from Stripe, then we need to ensure that the value of the transaction is not less than $0. I don't want negative transactions. So something like that, you can implement that. Also, we want to provide mechanism for full transparency. So for that, what we are doing is we are building all of these DLQs, all of these DLQs for SQS, SNS that are used internally. We are exposing them through a Datadog dashboard. So anybody in the company can look at the health of the messages, and if they have some messages that are stuck inside of that, let's say, messaging queues, they also have API actions to let them retry those failures for a certain amount of time. If they do not, then we will have to intervene. So what I've tried to do is I've tried to talk you through the entire process of how a problem statement was figured out, how we went for a certain, let's say, paradigm, why did we make choices for certain of the services, and how this stuff came together, and how this entire process that we talked about, this is nothing but solution architecture. So if tomorrow somebody tells you what a solution architect does, this is what they does, right? So this is their core job. A solution architect should be able to ask the business people, what are the constraints, what are the use cases, what are the things that we really want to do, what are the things that I can be okay not having in the system, what are non-negotiable. And once you do that, you can use those to make these decisions that we did in this process. So I could have used Kafka as an ingestion point because Kafka was like universally available, but it did not fit into my constraints of building it frugally, because Kafka would require me to basically have some servers running all the time, right? So it did not fit into that ecosystem. But if this solution was for some other company where Kafka was already there, it would have been a no choice, no brainer. So I've tried to talk you through the ecosystem, through the process of how a solution architecture could be thought about. Some key takeaways from this process was, then people basically asked us is, when should I build a data lake that is centralized, like one for your company, or I should have multiple of these data lakes? So for me, it works if you need to centralize. In our case, we had to centralize because we wanted this to be the single source of truth for the entire organization. So in that particular use cases, you should centralize this. But if you are utilizing data lakes just as a landing zone, like a temporary place where the file comes in and you want to read the schema and decide what we want to do, then you can decentralize it. So then multiple of your application systems can have their own small-ish data lake and they can be okay with it. But in this our use case, centralization was required. A key thing with data lakes is we need to pay really good attention to UX and DX. When I say DX, developer experience, user experience, because data lakes are notorious for becoming, they are really hot when they are launched in a company. People will use them for a couple of months and then they will forget about it. So it becomes just a place where something comes in, nothing goes out. So in order to make sure that it does not happen to you, make sure that you are having you have the personas in mind that you're trying to build, and build the interfaces that are required by those personas. So in my case, there was analysts that I was catering to, and analysts are good with SQL. So we utilizing Athena in this particular process meant that I am serving my analysts okay. At the same time, when I said that I want to help my developers, I created API actions that they can use, so they don't have to rely on a person to fix their errors for them. So my developers are happy at the same time. Again, I have already mentioned this. If the poor UX, then data will turn into data swamps, which is basically data just goes in, nothing goes out. There is also a little bit of limitations when it comes to open table formats. So if you are building data lakes, and if you search on data lakes right now, you will hear that there is Apache Hudi, there is Delta Lakes, and there is Iceberg. Again, two of them are Apache projects, and Delta Lakes is something that Databricks kind of presented that lets you do ACID, let's say, transactions on top of data lakes. So if you intend to use some of those services in your data lake, then and you want to manage that data lake through lake formation, then Iceberg is the only protocol that is mostly supported. It also has a lot of limitations, but that's the best format that you can use if you're in AWS ecosystem and you're building your data lakes. With that said, thank you very much for patiently listening to me. I hope I didn't bore you to death. And if you would like to have, if you have any questions, please ask them right away. If not, please connect with me on LinkedIn if you want to ask me some questions later. Thank you.
Thank you, Anurag, for your presentation. And there are two questions
Sure.
on Slido. AWS can become notorious with costs. While building this data lake, did you do any architecture changes to reduce pricing?
Yes, yes, we did. So in the process, if you see that there was this component called as glue crawler. Now this glue crawler is required in order to make sure that Athena can query on your S3 lake. Now, how frequently you run that crawler decides how much cost you're going to pay. So we looked at the patterns on how analysts were using that particular querying. We saw that, okay, most of the analysts were coming in onto the lake and querying it every morning, right? So I didn't need to have that crawling done every 15 minutes. Instead, we deferred it to 2 hours. So again, lessen the amount of the stuff. Another aspect of it was when we were looking at the data lake in S3. S3 is also, sure, it's not that costly, but it gets costly. So we put on life cycle mechanisms in which data that is in S3, which is greater than 6 months, it went into cold storage, which is basically Glacier. So you have this auto life cycle mechanisms that S3 provides. When after certain criteria, you can move your data from hot S3 to, let's say, cold S3. So in that way also you can we were able to manage some of the storage cost. DynamoDB, we put TTL on the temporary database that we were using in between. All of the databases that were temporary in nature, the TTL for them were from few hours to 24 hours. So if the data is registered well in the data lake, I don't need it in the temporary place. So that data goes away in 24 hours. So you're not paying for the storage costs. I think that those are the top of the things that come top of my head that we kind of did for cost optimization. Yes.
Okay, thank you. There's another question. So, what approximate size was the S3 object store in the end of the day?
Yeah.
Did you run into scaling challenges?
Yeah, so within 6 months, we were, I cannot say the exact numbers, but we were in hundreds of GBs of data that was plain text that was stored. And if I consider other data, other let's say things like images and all of those, we were close to 1 PB. 1 TB kind of data. Again, it's not a big scale, but it's gonna grow because it's only 6 months, 6 months old right now. So the scaling issues that we particularly had was with the lake and Athena. Like Athena is also, you pay for Athena for the number of queries you make, and you also pay for the amount of data that Athena scans in your query. So we had to put some best case, let's say we had to teach our analysts that you need to limit the scans by using the month, day, and hour partitions. So if you do that, you'll be able to reduce some of that particular cost. That was a big bottleneck, because if you didn't put that where clause with this thing, it would scan the entire 100 TBs of data to give you the result, which was like really costly. At the same time, it was slow. And this is exactly why we started looking into previously when I talked about Iceberg, Hoodie, and Delta Lakes. This was the reason why we started to go into that particular route, because if you store, so we were using CSVs and Parquet as the storage format for the data lakes right now. But if you use Apache Iceberg, it has a natural compression algorithm built in, where when we tested it out, it took the 50 gigs of data and compressed it to 5 gigs. So we are looking at those avenues in order to reduce and try to use the Hoodie's capabilities or Iceberg's capabilities to reduce those overheads. I wouldn't claim that we are successful, because we are hitting the limitations of AWS Lake Formation, and Lake Formation is a little behind in the curve when it comes to supporting these 3 open source table formats.
Okay, thank you. Are there any other questions here in the audience?
Yes.
Hello. So, question is, did you done some research in the market, and maybe some other platforms have this solution?
They do. I mean, Databricks is a great example. So if you, again, this was a small team. This is kind of came up as a POC that turned into a production kind of use case. One big area that we thought was Databricks. There are a couple of other vendors who are building something similar, like a managed data lake, but then again, we didn't want the data to go out of our control at this moment. We didn't want the account to be in somebody else's control. So Databricks, you can still, if you have Databricks, you can put Databricks in your AWS ecosystem through Marketplace. So it does not leave your ecosystem. So Databricks was definitely something that we considered. We also considered basically scrapping all of this and bringing in a combined paradigm, which is Lakehouse, in which certain of the data before processing is in data lakes, but the moment it is processed or there is certain business criteria that is met, it goes into a data warehouse. But all of this we never considered going outside of our control. So Databricks was the only choice, but there are other companies like OneSource and a few others that provide data lake commercial software, if you like to call them. I don't know what the right word is, but yeah, you can buy something from them and it gives you some more optimizations on top of data lake.
Yeah, sorry, I've overseen one question on Slido. What's different between data lake and big data?
Yeah, so big data is like the name that was coined when the data scale got really, really big. And data lake is just one of those architectural implementations that you see. Data warehouse is an architectural implementation. Data lake is an let's say big data implementation. So in general, it's a bracket term, data lake, big data, where it was invented around 2000s when the scale of the data became immense, and they just didn't have any other smart way of saying it. They just called it big data.
Okay, any other questions? Thank you very much for your insights, and yeah, this is your applause.
Thank you.